Okay, now having finished the carbonyl compounds, we move on to two other types of compounds. First one is nitro compounds, and it's one of the most frequently encountered type of functional group in organic molecules, such as nitro, benzene, which is one of the simplest molecular system we know, which contains nitro group, functional group. Okay, so and as you know, the nitro group can have this typical intermediate resonance structure, where one of the both the nitrogen and oxygen bonds have partial double bond character, bearing or having the pi electron density shared between these two nitrogen and oxygen bonds, whereas the nitrogen atom has got a positive character. Okay, so as a result, and the vibrational frequency, nitrogen oxygen vibrational frequency, usually comes between a range of 1530 to 1600 centimeter inverse, where you can see two bands. One for symmetric stretching and one for asymmetric stretching. Okay, so the symmetric stretching vibration for aliphatic nitro compounds usually comes between 1300 to 1390 centimeter inverse, whereas asymmetric stretching vibration usually comes between a range of 1530 to 1600 centimeter inverse. Okay, for aromatic nitro compounds, the symmetric stretching vibration of the nitro compounds, the nitro functional group, comes between 1350 to 1355 centimeter inverse, and for asymmetric stretching, it comes between 1490 to 1550 centimeter inverse. So you can see both the symmetric and asymmetric stretching vibration frequencies for aromatic nitro compounds is lesser than that of aliphatic nitrogen compounds. And if you think about it, you can find the answer very easily why is it happens so. Okay, and this one is a IR spectra of nitro compounds such as 2-nitropropane, and just like that we have discussed before, the symmetric stretching vibration of the nitro group here, both these two bonds here and now bonds here, usually happens between 1300 to 1400 centimeter inverse. Okay, and the asymmetric stretching vibration, okay, where one bond compresses and the other one stretches out, happens between a range of 1500 to 1600 centimeter inverse. So these are the major dominant band systems of nitro compounds here. Okay, and the rest of the bands are being contributed by the hydrocarbon part of the molecule. Okay, and the other type of functional group we discuss about nitriles. Okay, C triple bonded. Okay, so for nitriles, the C triple bond and vibration usually happens at around 2250 centimeter inverse. Okay, this is due to I'm talking about the symmetric stretching vibration, and this again depends upon conjugation, because the double bond pi bonds in here between carbon and nitrogen can take part in conjugation with other pi bond systems. Okay, and this vibration frequency usually falls in this region because the reduced mass of carbon and nitrogen are not much different, and though there is a slight difference between electronegativities of carbon and nitrogen. Okay, and because of the difference in electronegativity between carbon and nitrogen, the carbon nitrogen bond between in the nitrile system is slightly more polarized rather than between carbon triple bonds. Okay, and this change polarized triple bond, actually when it vibrates, the dipole moment changes to a significant magnitude, making the band of a significant intensity. Okay, so this one is a typical intense strong band, which is actually very narrow for the stretching vibration of a terminal nitrile functional group in propionitrile. Okay, so you can see, other than this band, the rest of the bands are due to the hydrocarbon part of the molecule. So we are almost coming to the end of IR spectroscopy, and you don't have to remember all these band structures and all the values, but you should at least remember some minimum things. Okay, so the first thing we have talked about before, you need to notice the shape of the bands, whether it's a broadened, really broadened band. Okay, if it is a really broadened band which comes around above 3000 centimeter inverse, usually due to OH and alcohol function group or carboxylic acid. And if it is a W-shaped band about 3000 centimeter inverse, that is due to a primary amine. Then if it is a V-shaped band at the same region, that is due to a secondary amine. And if it is a something like a very sharp spikes, that is due to CH of a sp hybridized carbon, okay, carbon hydrogen bond, okay. And if it comes out as a shoulder to a band system, then that is due to CH of a sp2 hybridized carbon. Okay, so we have already talked about the shapes. Okay, then right now coming to the values, you need to see the trend of the values. Okay, you need to at least remember these values and see. You need to have logic of where to find these values. Okay, so we start with the function groups that shows the vibrations at a higher frequency, such as OH. Okay, OH shows vibrational frequency above 3000 centimeter inverse, or sometimes starts from 2500 centimeter inverse and goes all the way up to 3600 centimeter inverse. And NH, such as the one in primary amine or secondary amine, shows bands at a 3400 centimeter inverse. OH is a very broadened band, whereas for NH in primary amine is a W-shaped band, NH in secondary amine is a V-shaped band, or rather a U-shaped band. Then the carbon hydrogen vibrations usually comes around 3000 centimeter inverse. So we start with the CHO here, carbon hydrogen vibration CHO aldehyde, that is usually being seen at as a doublet due to Fermi resonance, one at 2850 and the other one at 2750. Then when we come to sp3ch, we see bands between 2800 and 2900 centimeter inverse, okay, just below 3000 centimeter inverse. Above 3000 centimeter inverse, the CH vibrations are primarily due to sp2ch and sp3ch. sp2ch vibrations are seen at around 3100 centimeter inverse, and SPCH vibrations are seen at around 3300 centimeter inverse. Okay, if you remember correctly, the sp3ch vibrations are a set of high intensity bands. sp2ch vibrations are again a set of high intensity set of bands, but not as much intense as the SPCH bands. Okay, and the SPCH bands are really it's not actually a set of bands, it's actually a very sharp spike type band at around 3300 centimeter inverse. So it's easy to distinguish these band systems. Then again, for CH bands, for methyl and methylene functional groups, the CH bending vibration usually happens at around 1465 and 1365 centimeter inverse respectively for CH2 and CH3. Then nitrile systems, C triple bond N comes at around 2250 centimeter inverse. That's pretty easy to identify because there is not much difference in the reduced mass of carbon and nitrogen, so therefore it comes close to the frequency range of C triple bond C, okay, which comes at around 2150 centimeter inverse. Then carbonyl is typically around 1750 centimeter inverse, okay, and we shall start with the lowest frequency one, the amides. Okay, the amide shows carbonyl at around 1690 centimeter inverse. Acids show at 1710 centimeter inverse. For reasons we know, ketone shows at 1715 centimeters inverse. So if you take ketone as a benchmark, above ketone we have got acids and amides. Below ketone we have aldehyde, which shows frequency at around 1725 centimeter inverse. For ester carbonyl, frequency comes at around 1735 centimeter inverse. For acid chloride, the frequency is at around 1800 centimeter inverse. And anhydrides, okay, which shows two peaks due to mechanical coupling of the two carbonyl functional groups. Okay, then C double bond C, okay, you can expect this one in aromatic ring systems as well as sp2 carbon double bond systems in non-aromatic ring systems. Okay, so for the major difference between them is that for aromatic systems such as benzene, the C double bond C vibrations shows up as a set of bands between 1400 and 1600 centimeter inverse. Okay, but for systems other than aromatic ring systems, CWC usually appears, say for example, for vinyl system, appears as a single sharp peak between 1400 and 1600 centimeter inverse. Okay, then carbon oxygen bond vibration usually shows up at around 1100 centimeter inverse. Okay, then again carbon halogen, for example carbon chlorine bond vibration usually comes at as an intense peak, very intense peak at around 8 between 900 and 1000 centimeter inverse. Okay, so how do we, when we get an IR spectrum, how are we going to find out the peaks and interpret the spectrum? So that is a question. Okay, so if you need to find out the molecular structure from a given IR spectrum, you should start to look for peaks. Okay, but you can develop a protocol to look for the peaks, or a methodology, or an a typical format. Okay, to look how, or to look out for how to find out the peaks, and how to assign the peaks to a typical bond or a typical functional group. Okay, so a good rule of thumb is that, for me personally, I start looking for OH first, whether the molecule has got an OH. It's very easy to distinguish the OH functional group band from other bands. Okay, because OH band is really broad. Okay, so if you have a OH band, then obviously it's either an alcohol or a carboxylic acid. Okay, so then if there is an OH, then I look for carbonyl band. Okay, C double bond. Okay, so when we look at the carbonyl band, if you see that there is a band at around, sharp band at around 1700 centimeter inverse, or somewhere around 1700 centimeter inverse, then if there is a band, such a band, then see whether the band is split into two, such as a doublet structure. Okay, if there is a doublet structure, it's most probably an anhydride which contains two carbonyl functional groups. Okay, so if there are not two bands, but instead we have only one band, okay, then there is one carbonyl functional group, then what you do is confirm that there is the OH, okay, which we have already looked in the spectra already in the beginning. Okay, so if there is a band for OH as well, then we have band for CO, carbonyl functional group, and OH. Okay, then we have an carboxylic acid. So, but if the band is absent, OH band is absent, then look for, in the same region, okay, around 3400 centimeter inverse or 3300 centimeter inverse, look for the bands of NH. Okay, NH2 or NH. Okay, for NH2 we see a W-shaped band at 3300 centimeter inverse. For NH we see a sharp V-shaped band at the same range. Okay, so if there is such a band, NH2 or NH is most probably a combination of carbonyl and NH. Okay, that, or NH2, that makes it an amide. Okay, it could be an amide most probably. Okay, then if there is no such band, look for CO band between 1000 and 1200 centimeter inverse. Okay, so if such a band is there, it could be carbonyl and CO, makes it an ester functional group. Okay, if there is no such a band, then look for the CH band. Okay, CH band, that means the CH vibration at around 2790 centimeter inverse. Okay, but which appears as a doublet due to Fermi resonance of the bending vibration of the carbon hydrogen bond of the CHO functional group. Okay, so if there is a doublet at around 2000, something like a 2750 and 2820 centimeter inverse, then it could be a aldehyde functional group. So if none of these bands are present, then we have only carbonyl functional group. It could be a ketone. Okay, so but when we look for the carbonyl functional group, if there are no peaks for carbonyl functional group, then look for other functional groups. Okay, look for the band of OH. If there is an OH functional group, but if CO is absent, then it's an alcohol. Okay, so the same protocol we follow here. If there is no OH and no CO, look for NH. Okay, if you see a W-shaped band at 3300 centimeter inverse, it could be a primary amide. If you see a rather sharp V-shaped band in the same region, it could be a secondary amide. Okay, if none of these are present, look for CO bands at around 1000 to 1200 centimeter inverse. Then Then if it's just a CO band without carbonyl, it could be an ether. Okay. If this is not present, look for C triple bonded. Okay, CN at around 2200 centimeter inverse. Okay, a sharp band, a very sharp band. Then it could be nitrate. Okay, and if that is absent, look for C triple bond C. Okay, a little bit lighter, smaller frequency compared to C triple bond. Then it could be an alkyne. Okay, if this is not present, look for C double bond C vibrations between a range of 1400 and 1600 centimeter inverse. Okay, if there are multiple peaks, it could be benzene or aromatic ring system. If there is just one peak, it could be an alkene. Okay, if none of these bands are present, look for nitro vibration. Okay, look for two vibrations, the symmetric switching vibration at around, the sharp peak at around 1300 centimeter inverse, and another vibration, okay, at around 1400, between 1400 and 1500 centimeter inverse. Okay, which is the asymmetric switching vibration. If two such bands are present, that could be nitro compound. Okay, if none of these are present, look for a sharp intense peak at around 1000 or between 900 and 1000 centimeter inverse. It could be due to the carbon chlorine bond vibration, so it could be halide.